Okay, this is it, the last lesson for Calc 1 for summer 2020. It is day 18, chapter 5, section 4. And no mistake that this last section is about work. You have put so much work into this, and I am so proud of everybody, how hard that you have worked. And today, hopefully, if you have a little bit of a physics background, then this will be a little bit easier for you. But even if not, I think you'll be all right. First, we're going to talk about force and Newton's second law of motion as a product of its mass times its acceleration. Now, if you recall, acceleration is a second derivative. So that's why we have the second derivative here. So in the SI metric system, mass is measured in kilograms. Displacement is in meters, times in seconds. And the force will be in newtons, which is newtons will equal kilograms times meters per second squared. Again, we have a mass times our acceleration. So the force of 1 newton acting on a mass of 1 kilogram produces an acceleration of 1 meter per second squared. Now, it's interesting in this book, they bring up the U.S. Customary system found in the fundamental unit chosen in the unit of force, which is the pound. So in this case, constant acceleration, the force is also a constant, and the work is defined to be the product of force and the distance of that object moves. So work will equal force times distance. And if F is measured in newtons and D in meters, then the unit for work is a newton meter, which is called a joule. If F is measured in pounds and D in feet, then the unit for W is called a foot pound. And that's about 1.36 times a joule if you need to convert it. I have to say, this is the first time that I saw a book where it brought that out in calculus, looking at the U.S. customary measurements as well as the metrics. So that's kind of neat. All right, so how much work is done in lifting a 1.2 kilogram book off the floor to put it on a desk that is 0.7 meters high? Now, we need to use the fact that acceleration due to gravity is 9.8 meters per second. In order to lift something, we have to have it be the same exertion of gravity. So we're going to take a look at that 1.2 kilogram book times that 9.8 gravity, because then we have to equal that to move it. So how much work will be done? Using that fact, we're going to take that 11.76 that we just discovered in newtons, and we're going to multiply it by the height in which we lift the book. So remember, we're taking this 1.2 kilogram book, lifting it off the floor to 0.7 meters high. So that is why we take that. Then work would be the force times the height. So that will equal 8.2 joules. Here in B, we're asked how much work is being done in lifting a 20-pound weight 6 feet off the ground. How much work is being done in lifting a 20-pound weight 6 feet off the ground? Well, here we have work equals our F times D again, and here we have 20-pound weight 6 feet off the ground. So we would multiply the two and have 120 foot-pounds. Now notice in part B, unlike A, we didn't have to multiply by gravity because we were given the weight, which is a force, and not the mass of the object. So very important, because we were given the weight, we didn't have to multiply by our gravity. Okay? All right, so as you can imagine, when we get down here, we're taking a look at, once again, integrating as we go from 1 to n. We're going to take the integral, the same thing that we've been doing in the last few sections. So we have to define work in moving the object from A to B. So you're moving the object from where it starts to where it ends. As the limit, as n approaches infinity, since the right side is a Riemann sum, we recognize it as a limit being a definite integral. So from A to B of f of x dx. Nothing new, just another application that we can use here. So example 2 says a particle is located at a distance x feet from the origin. So you have this particle that is located there. Now, the force of x squared plus 2x pounds acts on it. How much work is being done in moving it from 1 to 3? So here we have our work from 1 to 3. We have our force being x squared plus 2x dx. We just integrate it, and then we evaluate it, throwing 3 into it, minus our 1, and we will get 50 over 3. So the work done is 16 2/3 foot-pounds. Now, the next example, we're going to look at Hooke's law, which states that the force is required to maintain a spring stretched x units beyond its natural length is proportional to k times x, where k is a positive constant called a spring constant. Hooke's law holds provided that x is not too large. So we'll see what too large is. Example 3, the force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15. So we're just moving it 5 centimeters. How much work is being done in stretching the spring from 15 to 18 centimeters? Now, according to Hooke's law, the force required to hold the spring stretched in there will be k times x. So when the spring is stretched from 10 to 15, we're talking about 5 centimeters. And if we want to look at that in meters, that would be 0.05 meters. So that means we're going to plug 0.05 meters into our function and set that equal to 40. So using our formula, we have 0.05 times k will equal 40. So we can see that our k value then is 800. Once we have our k value, we know that f of x will equal 800 times x. The work done in stretching the spring from 15 to 18 centimeters would be here. So we have from 0.05 to 0.08, 800k dx. We're going to integrate that again, simple integration, and we will evaluate using our upper and lower bounds, and we will find that we get 1.56 joules. Okay? So far, not too bad. Now let's take a look at example 4. Talks about a 200-pound cable. It's 100 foot long, and it hangs vertically from the top of a tall building. How much work is required to lift the cable to the top of the building? All right, so here we don't have a formula for the force function, but we can use an argument similar to that one in definition 4. Let's place the origin at the top of the building. So the origin of 0 is going to be at the top of the building, and x pointing downward as in figure 2 here. We divide the cable into small parts of length delta x. So again, similar thing, we're going to divide it into delta x parts. If you can see that here, that's what this little segment is showing. If x sub I asterisk, which we had talked about before, is the point in an interval where it will actually hit that function, were lifted approximately the same amount, namely x sub I asterisk. The cable weighs 2 pounds per foot. So the weight of the ith part would be 2 times delta x. So the work done at the ith part in foot-pounds would be 2 times delta x, this is our force, times our distance. So we'll have 2 x sub I asterisk delta x, and we need to integrate that. So once we integrate that, of course, as limit as n approaches infinities, because we want to take a look at as many little segments as we can. So we're going to go to infinity once again, and that will become a definite integral from 0 to 100, because that is the length of our cable. So integrate this, it's just x squared, plug in our 100, and we get 10,000 foot-pounds. Of course, we plug in 0, we get 0, so we just get 10,000 foot-pounds as our answer. Okay. Lastly, but not leastly, well, I guess maybe last, but you can decide if it's least. We have a tank that is in the shape of an inverted circular cone with a height of 10 meters and a base of radius 4 meters. It is filled with water to a height of 8 meters. Find the work required to empty the tank by pumping all the water to the top of the tank. The density of the water is 1,000 kilograms per meters cubed. So let's look at this solution. So we have to measure the depths from the top of the tank, introducing a vertical coordinate line. And we take a look at figure 3. Let's take a look at figure 3 over here, which they give a nice illustration. Here we have the top. Here we have where it's filled. This is 2 meters because we filled it up to 8 meters. We know that the total is 10. Okay. So we were looking at the interval from 2 to 10, because this whole thing is 10. So we're going from 2 to 10. So we have a distance of 8. And we're going to cut those into sub-intervals, all these little tiny sub-intervals. And of course, we're going to once again realize that we're going to take the limit as it approaches infinity. And we know from the previous section that we have our pi r squared times our width, our delta x here. And our pi r squared, our r in this section would be 2/5 times 10 minus x sub 1 or x sub I asterisk. So again, I'm going to take a look at here. We're going to compute r from similar triangles. And similar, trying to see if I can get them where you can see them both. Yep, right here. So here's our similar triangles. This is 10. This is 10 minus x. So our radius would be 2/5. You say, how do you get 2/5? 4 over 10. 2/5 times 10 minus our x sub I asterisk. Okay, so this is what we're going to use for our similar figures, and that'll give us our radius. So we're going to plug that radius, the 2/5, 10 minus xi asterisk in here. Remember, it's radius squared, so that's why it becomes 4 pi over 25, this squared. And we have our density times our volume, so we have to make sure to make it our volume, we have to add our delta x in here as well. Okay, so now let's reduce this because we have some reducing here to go along with it. We get 160 pi times 10 minus x sub I asterisk. We still have our delta x. Now, the force required to raise this layer must overcome the force of gravity. So we have to put our 9.8 in here. So we have our 9.8, 160 pi 10 minus x sub I asterisk squared, and then our delta x. Okay, after I simplify this a bit, We must realize that each particle that travels will be approximately x sub I asterisk. We know that. And our force would equal what we just simplified as an expression times x sub I asterisk. So now we have to include that in for our work function. We have our work function. No surprise, going from 1 to n as n approaches infinity, we are going to look at it as the integral from 2 to 10. Remember, we're not starting until 2 feet or 2 meters down, and then the 10 meters. So we're going to integrate this. Taking out some of the constants here, we can make sure that we take out the 1,568 pi on the outside. Integrate the inside, we get 50x squared minus 20x cubed over 3 plus, excuse me, x to the 4th over 4. And we're going to evaluate that between 10 and 2. So plug your 10 values in, minus plug your 2 values in. And once you have that, you will get approximately 3.4 times 10 to the 6 joules as your answer. Okay? Guess what? That's it. We're done. So I would encourage you probably to watch this video again because there's just, it depends on how much physics background you have, but might be a lot of new things that are put in here. However, we're definitely using the same concepts as we used in the last few sections. So I will say thank you for your attention through this whole course. And I will talk to you during the exam.